can start. Hello, everyone, and welcome to the Inform ROS webinar. And my name is Pei Ran. I'm from Beijing Jiao Tong University. And today we have exciting to kick off our first webinar of this year. And I'm honored to have Dr. Yili Tang from the University of Western Ontario as our first speaker. She will sharing her insights on the passenger community in urban rail transit from behavior and data intelligence in science. And Ili now is the assistant professor in the Western Ontario, leading the mobility technology research group. He has also been an officer of ROS for years. If you have any question about ROS events, please feel free to reach out me or Ili. And then now today's presentation will run like 40 minutes and followed by a Q&A session. If you have any question during the talk, please drop them in the chat. We will address them at the end. And thank you all for the joining, and let's welcome Yili. Please go ahead.
Thanks, Pei Ran, for the introduction, and thanks for having me to present our study set for the insights of passengers commuting that in urban rail transit. I'm currently the assistant professor at University of Western Ontario, specializing in transportation. I'm also the ROS treasurers last year, and currently I'm the ROS secretaries. So in the following ROS international webinars, we will also host a variety of the speakers as well as their work and studies that from different countries as well as from our officers, and also feature our new ROS problem-solving competitions this year. So today's webinar that I will talk about some of our analysis and insights when we're looking into the passenger commuting that in the urban rail transit. So commuting problems has always been a concern that in the urban rail transit, especially that in the metropolitan areas. So from the transit agency side, that there is a significant demand variations in peak and off-peak hours that in many of the major transit commuting systems, such as in Hong Kong, New York, Toronto, Copenhagen, and also in Sweden. So when we are facing the overcrowding that during the peak hours, this may increase the safety and security risks for the transit agencies. Such as the safety for passenger to move around, as well as operational perspective for the transit agencies to have proper operations and also control the vehicle frequencies. On the other side, the insufficient utilization during the off-peak hours will also induce the resource utilization concerns, where that the high operation costs during the off-peak hours may also create the issues that for the operating concern that for the agencies. On the other side, that when we're looking into the passenger perspective, overcrowding often may induce a denied boarding, such as the picture that we see in the middle. So denied boarding can decrease the transit user satisfaction, and also that may also repel them to choose to the other service routes, to the other transit mode. It is also unclear about the impacts of the operational changes to passenger behaviors and system dynamics. In some major urban rail transit systems, that we often see that a peak demand can consist of 47% of total passengers during the day. And in some busy stations, we can also see this percentage up to 60%. So today's webinar that I will explain and introduce some of our behavior models to model the entire urban transit system that's through the line, and also to provide insights on the upstream boarding patterns to the downstream boarding patterns, and to understand passengers' behaviors on the system crowding and congestion. So when we are looking into a glance view of the passengers' behaviors that in the transit network, We can see that transit networks usually that we will have a series of the service rounds that depart at a scheduled time. So this is the abstract graph that you show how the rail transit networks looks like. So when the train departs at T1, that it will go from the first stations to the last stations, and a series of the service round will be operated that in the transit line or the transit network. So from passenger side, when we are looking into the commuting, especially for morning commuting, passengers will incur a list of the trip cost, and they will make their choices of departure time based on this trip cost. Some typical trip costs including their scheduled delay cost. So if passengers have a preferred departure time, such as T star that we see here, then if passengers take the T star, they may incur a very high crowding and also queuing cost. In this case, that passenger will choose to depart early or depart late. But then this means that they will change their scheduling, their preferred scheduling, and then passenger will incur a schedule delay cost. And on the other side, for each of the service rounds, passengers will have also incur a crowding cost, depending on how many people are in each of the service rounds, as well as a queuing cost if the service rounds is overcrowded. So some passengers may need to wait for the next trains to come in order to get on board. Fare cost is also a common cost that passenger considers that when they're making their departure time choices, as well as in-vehicle time cost. The preference of passengers' trips, as well as their origin destinations, the length of their trips will also affect their departure time. It especially affect their flexibility of the departure time. So one of my study and our team studies are focusing on how can we model this cost and how can we transfer the individual passenger behavior to understand the impacts on the systematic crowding and the systematic congestion and queuing that in the urban rail transit. First, the specific methodology that we develop is we are alleviating the game theory perspective, where that we want to understand and quantify each of the trip costs for passengers. So we can develop the mathematical formulations for each of trips, where the schedule delay cost, crowding cost, in-vehicle cost may depend on each individual passenger's origin destinations, as well as the number of passengers, total number of passengers on board. So ultimately, that this will direct us to derive user equilibrium conditions for the passengers, such that if an entire system, an entire urban rail network system, achieved the user equilibrium, then for each origin destination pairs, the number of passengers that taking the service round to achieve their destination will now be able to reduce their trip cost by unilaterally changing their departure time. So this can be mathematically expressed as a function that we can see on the right upper equations here. So if we observe that there are some passengers, there are some service rounds has passengers, then these service rounds will have the same equilibrium cost of the other service rounds. The second equilibrium condition is that if there is a service round that is unsaturated, then there will be no queuing cost. And if there is a service round that is oversaturated, then the queuing cost should be no less than 0. So this is corresponding to the reality that when a train is at a full capacity, then passengers will need to wait for a next train to come in. So this will incur additional queuing cost. And mathematically, we can express this condition as in the right side of the equation here. So this equilibrium condition basically that will help us to solve the distribution of the number of onboarding passengers for each origin destinations and in each service routes. And this equilibrium condition will also help us to transform from the individual passengers' behavior, because passengers will choose their departure time choices based on their individual trip costs, as what we can see before here. And this individual trip cost, when there are more and more passengers select a specific service routes, or let's say their preferred service routes, then the crowding cost or queuing cost in these service routes will be increasing. And the increase of these service routes will ultimately also affect passengers' individual departure time choices. So in this case, there are endogeneities between the passengers' individual trip cost to the systematic effects on the service routes crowding and service routes queuing time. So, and these equilibrium conditions can be further described as a list of inequalities that for the system conditions for the passengers. So the first two that's showing when passengers are taking the service round, then this corresponding to the first equilibrium, user equilibrium conditions, that no passengers can reduce their trip cost. So the list of these components that in the first two equations indicate that if a passenger, so here, that if a passenger have amount of the generalized trip cost, and this generalized trip cost is greater or equal to the equilibrium trip cost, then the number of passengers that are going to take this service rounds will be 0, because in this case, it will be more it may be more cost effective to take other service routes. And if there is a service round that have an equilibrium cost or trip cost that is same as the equilibrium cost, then the number of passengers taking these service rounds will be greater or equal to 0. The second corresponding to the queuing condition. If the service round is unsaturated, means that the number of passengers that taking this service round is less or equal to the total capacity of the service round, then the queuing cost will be 0. So if the number of passengers taking this service round is greater than the capacity, means that the queuing cost should be greater than 0. The last three inequalities indicate the demand capacity and definitional constraint. The first one is a capacity constraint. This capacity constraint indicating the cumulated onboarding passengers in each service round should be less or equal to its physical capacity of this specific vehicle. And the second is a demand constraint, means that the total number of passengers that are carried by all the service rounds in the urban rail transit should be equal to the total demand. So solving these inequalities will give us the distribution of the onboarding passengers that in each of the service rounds corresponding to each origin destinations. So now let's look into the case studies we conducted in the Copenhagen Metro. So this is a map that in the Copenhagen Metro, and the yellow line and the gray lines are the two busy commuting lines in the Copenhagen. Now we pick up the 5 busy stations that in the Copenhagen Metro, and then we will use the behavior modeling simulation the method to understand and simulate what is onboarding passengers and the crowding as well as the queuing conditions that in this commuting line. So with these 5 stations, we collect the origin destination demand. So this table, the table on the left upside, that is a origin demand matrix that we collected from the Copenhagen Metro. So we can see that the demand varies between origin destinations. The largest demand is coming from the Nørreport station to the Kogan Nortor station. This origin destination is also a very busy commuting origin destination that is used by passengers that in the Copenhagen system. The second input data that we are collecting is operational characteristic data. So this operational characteristic data tells us what are the in-vehicle time between the 2 stations. And these are yearly are the record that we collected from the metro agencies or urban rail transit agencies. Then there is a third category of the input data that we collect is the socioeconomic data and the service characteristics. So these service characteristics tell us the headways of each service rounds that are running in the urban rail, as well as the total number of commuters, which is a demand of this urban rail transit. And usually this demand can be, let's say, the demand during the entire morning peak hour, or the demand during the entire morning period, including the peak hour or off-peak hours. In this case, we are collecting the demand from the entire morning period, including the peak and off-peak hours. We also collect the input of the vehicle capacity, which is the physical capacity of the vehicle. For the vehicle used in the Copenhagen Metro, that this is the standard physical capacity is 275 passengers per service rounds. So that is the maximum capacity a train can carry. And within this 275, passenger will be able to have 120 seats to be occupied, and including 155 standing capacity. So the capacity characteristics will help us to formulate our crowding cost function. So that is one of the crowding costs that passengers considers when they're choosing their departure times that in the urban rail transit. So in this crowding for cost function, as we can see, is related to both the number of seat capacity and also the number of standing capacity. The rest of the characteristic we can see here is the social economic factors. So these social economic factors indicate what are the values of time for passengers when they're taking the urban rail transit, and what is the values of time if they depart early and if they depart late. So from the previous empirical studies from economics and urban rail transit economics, usually that the unit cost for passengers who choose to depart late have about 3 times higher than those passengers who choose to depart early. So this is aligning with a reality such as if we arrive at work late, basically we may have some penalties that in the work. So if we arrive at work early, so this penalty is less than arriving at work late. And this has been approved also, and this has been also shown the evidence from the empirical studies of passengers' perceived cost when they're taking a late arrival service rounds than taking the early arrival service rounds. So all this input data that will be the parameters of the mathematical functions and inequalities that we develop that in our behavior modeling. And by adding these parameters in the mathematical functions and the optimization functions, by solving that inequality that we developed before, we'll be able to derive a spatial temporal distributions of passengers' departures that in each of service rounds. So this shows a table of, for each of the origin destination, so OD12 means origin destination from origin 1 to destination, from station 1 to destination 2. And then in each station, for each of the departure times, how many number of passengers going to board on each of the service routes. For virtualization, we'll be able to see what is the increase, accumulated increase of the passengers in each of the service rounds and also in each of the stations. So this figure that shows, for example, that let's look at a specific service rounds that depart at 7:30. So for this 7:30 service rounds, we can see the cumulative passengers across the stations. So this yellow bar showing the station 3. So this is the number of boarding passengers in the station 3. And the green bar shows number of passengers in the station 3 as well, but with the different origin destinations. Then the orange one shows the number of passengers boarding in the departure time at 7:30 in the station 4, with the origin destination from station 4 to station 5. We can also see the differences of this passenger patterns when we're looking into more close to the peak hour. So if we're looking at a service round that depart at 8:15, there will be more passengers be able to board at 8:15, especially those passengers who are taking the service round in the upstream stations. And in this case, that we will see in the service round who departs at 8:15, the category of passengers from different origin destinations is more than passengers who are boarding in the shoulder period. And this indicates that the spatial distribution of passengers that in the urban rail transit. So now, looking into further that we'll also be able to derive the boarding patterns of passengers in both upstream stations and downstream stations. So in upstream stations, we can see majority of the passengers will be able to board in the central peak period. This is because upstream station passengers will have priorities to occupy the seat, as well as they will also have priorities that to enjoy a more comfortable seating and the less crowding that when they're taking the urban rail transit and taking the train. And gradually that when the capacity of the service round is occupied by the passengers, those passengers who need to board in the downstream stations, they have to shift to their departure time outside the central peak period. This is because first, that the central peak period service round may be already at a full capacity. So passengers may not be able to board on the service rounds. So they have to wait for the service rounds. Either they need to depart early or they're departing late. So then we can see the differences of boarding patterns for passengers when they're boarding in the downstream stations and then when they're boarding in the upstream stations. Now I'm going to move into a next subsections of how we validate these behavior models and how we engage with the trip data that we collected from smart card data to verify and further understanding the dynamics of passengers' boarding patterns in the rail system. So we have compared the modeling result with one of the stations, which is station 3, that in the Copenhagen Metro station that we labeled. So the figures in the bottom showing the cumulative departure time curves we collected from the smart card data. Several things checkpoint that we considered. So when we compare this with the smart card data, the peak hour starting time is approximately both at 7:50. So this indicate the accuracy of the behavior modeling to capture the peak hour starting time that in the urban rail system. The peak hour length is also captured about 1 hour. More importantly, when we're looking at a full capacity, which is a central peak period, we'll be able to recognize that overcrowding duration that in this Copenhagen Metro system is about 40 minutes to 6 minutes. This can be seen from both the smart card data as well as a behavior modeling perspective. We further looked into a passenger's side on it. So when we're looking into a specific passenger's patterns, we recognize that passengers actually have departure time flexibilities. So in the previous slides that I mentioned that yearly passengers will choose their departure time based on a variety of the costs. And from the smart card data, we can see that this kind of cost also varies, which means that there is a degree of the flexibility for passenger to choose their departure time. And from the smart card data, we can see this interval can vary between 10 minutes to 50 minutes. Some passengers, they may have a very rigid departure time, which every day they're departing almost in a similar time interval within 10 minutes. We also see that there is amount of passengers, they have a large departure time flexibility and can vary between 15 minutes. If we see one of the curve here, some passengers in some days they depart at 7:57 a.m., while in the other days, they can depart at 8:55 a.m. So this large range of the flexibility that provide insights of that we can further design operational strategies or pricing strategies to incentivize passengers to shift their departure time and ultimately can smooth out the peak hour crowding and peak hour congestion that in the urban rail systems. The diversity of passengers' flexibility on departure time choices can also be influenced by station locations or land uses as well as their trip purposes. So driven from this insight, we further looked into details of how can we describe and how can we define the passenger departure time pattern. One specific characteristic we identified from the trip data is that there are randomness also for passenger departure time. But there is also a patterns for passenger departure time. So if we see these two figures here, when we're looking at the patterns of departure time, these specific trip trajectories and trip record indicate this type of the passengers, they typically travel between 6:45 to 7:05 this time interval when they're departing, when they choose the urban rail transit as their commuting pattern. There is also some randomness here that some of the departure times that falls near the 6 a.m., which is quite early than their normal departure time patterns. So in this case, we need to identify those outliers and randomness for passengers' departure time in order to recognize their patterns of the departure time. So we adopted an outlier analysis, use the 3 theta criteria. So for any departure time which is outside the normal period, then we basically eliminate this record. And ultimately, we'll be able to get their departure time patterns. So for example, in this specific record, we can identify the departure time pattern is from 6:45 to 7:05. This is we consider the departure time flexibility. And ultimately, that we'll be able to derive the a variety of the difference of departure time pattern and flexibility. And when passengers have a different departure time patterns and the flexibilities, we can introduce this flexibility and patterns that into the dynamics of system. And that drive us further developed an integrated data-driven agent-based simulation, where that we consider each individual's passengers or each individual categories of the passengers into our system, and so that we can derive a more smaller granularity of the crowding of the departure time of the queuing time in the transit system. So in this agent-based simulation, we take the consideration of the individual levels of passengers in their departure time flexibility and also their trip record, as well as their typical trip patterns that in the urban rail system. So this will be one of our individual level data from the smart car data. We also involve the system level data, which is similar to the data we see before, such as the operational characteristics, the frequency of the vehicles, as well as the total demand for the passengers in the entire system. Together with the network data, how many lines we have in the transit system, the number of stations that in the urban rail transit system, and also if we have any transfer stations that will be identified that in the system. This agent-based simulation runs as a discrete time considerations, where that for each, the right side of this flow showing how we update the status of the agent-based simulation. So we first have the input of our schedule table. Then we also have the input of passengers, the time that entering the urban rail system. So every 20 seconds, or we can define either every 20 seconds or every 5 minutes, depending on how much granularity that we want to set for simulate and for understanding the dynamic of the system. In this case, let's say that we update the system every 20 seconds. then we'll be able to identify for each of the passengers after they enter in the system, where are they in the after 20 seconds? And the status of the traveler can be pre-trip. For example, they're still waiting at the platform, or walking to the platform, or board the train. And it can also be that they may at the transfer trip that in a next train. And ultimately that the last status for the traveler will be arrival. So for each 20 seconds that we will update the status of the travelers, that will help us to recognize where and when are these travelers that in the transportation, in the urban rail system. And let's look into a case study that we simulated a specific rail line set in the Beijing metro system. And this is also a commuting rail line that accommodate the commuters that during the morning peak. With the agent-based simulation, for the sake of time, I was specifically showing into these two stations that in this commuting line. So here are the comparisons of these two stations and the result of what we can get for each from the agent-based simulation by the individual level of the trajectory as well as system level of the demand data. So for the Nanshao station, which is the station which is here, so for the upstream stations, we can see that the overall plan for crowdedness is pretty low. This is because for the upstream stations, usually passengers have priority to occupy the capacity, and then the transit vehicle is still empty. However, when the train is traveling from the upstream station to the downstream stations, we'll see the cumulated crowdedness for the passengers. And the right side of the figure shows two peaks that in this station. There is a small peak in this station is because there is an incentive and discount of the fare before 8 a.m. So we can see it very apparently that before 8 a.m. that there is a small peak because there's a number of passengers that take advantage of this discounted fare. And after 8 a.m., the peak hour accumulated and even more. So this becomes a central peak of the stations that in this simulation and in this Beijing Metro commuting line. And we also see the differences of the peak hour conditions. The upstream stations, barely we couldn't identify the peak hour conditions. It's more of a flat line. But in the downstream stations, we can see a very apparent peak hour conditions. This also echoes the behavior model we see before when we're looking at the different onboarding patterns that shows the different peak hour patterns for upstream stations and downstream stations. So a very common question and also many of the and also feedback we often get is, while we indeed use the smart car data, the real world data, and we indeed make the updates and our simulation in every 5 or 20 seconds, then the ultimate question is, how can we really sure that the result we get here reflects the reality? So a validation method we proposed in understanding the passengers crowding, especially this when it's related to individual pattern, is we are comparing the entering time to the exit time for the passengers. So with the smart car data, in some of the gated system, we'll be able to, in gated system, we always will be able to get the entrance, in most of the urban rail system, we'll be able to get the entrance time of the passengers. In some of the system, we also will be able to get the exit time for the passengers. And from our simulation, we will also be able to simulate what will be the simulated exit time for the passengers when they're finish their trip. So comparing this exit time of passengers with the smart card exit time, then we'll be able to see what is the differences that between our simulated exit time as well as the smart card tapped out time. One thing I want to mention is that one thing I want to note is that for this validation, it is important that we validate it with the off-peak period data. This is because for the peak period data, passengers crowding and queuing will make its occupancy much higher than its physical capacity. For example, if its physical capacity is 1,200, however, in the peak hour, passengers will tend to squeeze into the vehicles. So in that case, the vehicle may accommodate more than 1,200, this design capacity. So it may end with 1,500, 1,000 with 900. And that is what we observed also in the reality. So to validate the simulation behavior modeling with a smart card with real data, it is very important to recognize the effects of the queuing and effects of crowding on the system. And to verify it with off-peak hours would be the first step, that to understand the logic correctness and accuracy of the simulation and the modeling perspective. And then we will further be able to validate it with peak hours once we have calibrated the peak hour occupancy in each of the service round. So here shows the differences of the peak hour and how the crowding and peak hour waiting time accumulated over time. If we're looking at this Shahe station, which is a downstream station of that cumulative line, so the waiting time can be up to 20 to 30 minutes. So this is additional insights that we can get from the simulation and the data-driven agent-based simulation, which we may not be able to measure it directly, that in the reality or in the real urban rail transit. And in most of the cases that in the urban rail transit, because of the dynamics and the flow of passengers that come in and come out, it is also very difficult to measure how many passengers are waiting on the platform, as well as what is the waiting time for passengers when during the peak hours. So from this perspective, the data-driven agent-based simulation will be able to provide this latent insights, as well as the additional insights to the transit agencies or operators to understand the degree and the severity of the crowding and the congestion during the peak hour. So to summary and to take over, that in general, when we are looking at the passengers commuting, especially in the urban rail transit, it is important to recognize their onboarding behaviors and onboarding patterns. And also because urban rail transit often expanding a large regions, the upstream stations and downstream stations passenger flow and onboarding patterns can be different. And these differences can further reflect the differences of peak hours, as well as the differences of the time varying crowding and queuing. This behavior perspective, as well as the comparisons of data and the data-driven simulation, will help the transit agencies to assess their operational strategies, especially when they want to implement a new scheduling or they want to implement a new vehicles with different capacities. Then the importance to understand how this operational strategy or scheduling going to affect the passengers' behavior, as well as the crowding effect, will be very important. And ultimately that it can provide a tractable cost-benefit analysis for each of the smaller granularity of time, as well as for each of the stations, that we will be able to identify how these onboarding passengers change and the patterns changing over time. And that is my seminar today. Thank you everyone for listening. I'll hand it over. I'm happy to take any questions and hand it over to Peiran.
Okay. Thank you, Yili. Thank you for a very insightful talk. And we have some question in the chat. And first, he will ask if we could use the human-centric approach to take passenger feedback towards their real-time problem and recertify this model provides the peak time and onboarding behavior of a passenger. Can you see the chat?
Yeah, thanks for the question. So definitely, one of the very important input and as well as the characteristics that we include in the behavior model is passengers' perceived costs, their values of time. So this yearly, when we need to conduct it. So let me show this here. The social economic factors that we're collecting from passengers. Sometimes we conduct a survey from passengers to understand what's their values of time that when they're taking the urban rail transit. Sometimes we also develop the human-centric approach where that we are designing the pricing strategies and also we are designing the scheduling to understand what is the impacts of this pricing on the different categories of the passengers who may have a different values of time and different social economic backgrounds.
Okay, if anyone has a question, you can just raise your hand and can unmute you. I have a personal question. And I want to ask that if this methodology can be applied to a larger scale of network, especially when some multimodal, we have the regional trains. There are a lot of commuters through the trains or maybe the urban transit to achieve their destination. So maybe some transfers between different model will be addressed. I'd like to hear your insights about this. Thank you.
Yeah, thanks, Peiran, for the question. That's a very good question. One of our ongoing work is to involving the multimodal, especially that for the data-driven agent-based simulation. When we are updating the traveler's location, the transfer will be very important, considering that we are looking into. And when we are involving the multimodal, the difference is that instead of we just have a rail transit scheduling table, we will merge the table of the rail transit with the other modes, such as buses or regional rail. And we will need to estimate. So in the simulation, we will estimate what is the probability for passengers to when they're taking the transfer to get on or to exit one system and then get on the next system. So this will also include, we will need to consider and calculate their waiting time to exit the station and then go to another transportation mode stations. And if the estimated arrival of passengers is less than the departure time, then this passenger will have a high probability to get on board for the other transit mode.
Okay, thank you. We have audience raise a hand. I will the question from Yuan Qu.
Hi, Kelly. Can you hear me?
Yes.
This is Yuan from the University of Hong Kong. So here I have two questions. First question is about the Copenhagen map of the railway system. So I have a question about this I noticed that there are two lines, the green lines and yellow lines, they share several stations, right?
Yes. Is it
So
that you're referring?
no, I mean the system in the Copenhagen.
Yeah, this one.
Yes, here. So here I noticed that the green line and yellow line share several stations here. And your model is defined by the demand for a certain line, M. So for this situation that several lines share stations will be a problem for modeling the behavior. For instance, if I'm a passenger on the yellow line, I may think this line is really crowded. I may just choose the station and just change to the green one. So would it be a problem?
So this depends. in the Copenhagen Metro, yellow line, and this depends on whether these two lines are in the same platform. So the model that we propose here is based on the platform perspective, based on the station perspective. So if these two lines are operating in the same platform, then what we do is to merge the scheduling timetables of these two lines together. And so that becomes a merged, integrated timetable for passengers to choose. So in that case, passengers will either choose service routes that in the yellow line or choose the service route in the green line. So in Copenhagen Metro, for these stations that they're in the same platform, so it is aligning with it doesn't induce the differences of the yellow line and the green line, but rather a matter of combined scheduling timetable. In some other metro system, they may have a different platform. If they have a different platform, this actually becomes two separate systems. And when it becomes two separate systems, they will not interact with each other. To consider two lines, the methodology is to merge the scheduling timetables if they're in the same platform. Does that answer your question?
Yeah, okay, got the point. That makes sense. Yeah. And another question is about the analysis about the Nanshao and Shaka station. So you show that the demand or the passenger on platform, they share quite different trend. So my problem is for this trending difference, it is because the crowdness, or the people who live in Shahhe and Nanshao are, I mean, in the different demand. Like for people, like for instance, if the people in Shahhe are like for students or for the commuters, for the programmers, they have some scheduled time they need to check in at a company. So do you check the difference about the local population and some geography information?
Yes. So the data-driven agent-based simulation that we look at directly the crowdiness and the queuing time. So this part that we involve the individual behavior from the smart card data directly. So this simulation doesn't contain the information about what their trip purpose and why they're having the crowdiness, but rather that we use this data-driven agent-based simulation to understand and quantify the congestion and crowding. So this is a part of the clarification. So back to your question, yes, indeed that the reason, so we did take a look about the land use and as well as the population surrounding the different stations that in that regions. In the Nanshao stations, it is more in the suburban areas. So there are less residential areas, and definitely in the Shahhe station, there are more residential areas. The important thing is that the important thing is that to identify what is the ground truth of the waiting time and the capacity and occupancy during the peak hours that in these commuting lines. Because in many cases that what we see some concerns and issue is that we know these stations are crowded, but we actually don't really understand how crowdedness it is. And it's also unclear to understand what is the waiting time during the peak hours. So by the data-driven agent-based simulation, we'll be able to quantify this and quantify it in a dynamic and also time-spatial ways, so that give overall pictures of the network for different stations on it.
Okay, I got the point. That makes sense. Because I noticed this problem because Shahhe is one of the most crowded station in Beijing's morning, right? So I may think about this would be a really unfair comparison to compare Shahhe with Nanshao, but yeah, I understand the point. Yeah.
Yeah. So the key point is that we really want to understand is Shahhe is congested, but how congested it is. So this AAAM will be able to help us derive this quantification on it.
Okay, thank you.
Okay, there is a new question from Carl Martland. And he said, my experience as commuter for 35 years in Boston shows that there is certainly an equivalent, but also it takes a couple weeks after school starting in early September to reach that equivalent. During this period, all commuter experience long delay and they figure out when to travel.
Yeah, that's exactly the case when we're talking about the equilibrium, especially for some regions where passengers may have or the population will have a concentrated purpose on it. And we also see sometimes when we have a new rail lines or new stations that just opened, then we'll see gradually there are some differences that in the first few months or first few weeks where passengers are still figuring out when and where to depart and what will the best choices to depart. And after that, when they get the full information from the system start to achieve to the equilibrium, where we will see a similar patterns every day that for the peak and off-peak hours. Thanks, Carl, for pointing out this.
You're welcome.
Okay, it seems like we don't have any more questions, and we have been around for 1 hour. We will conclude here, and thanks, Ili, for your talk, and thanks everyone for joining us. And the recording of the video will be available afterwards. We will send the link to you. You can also check the YouTube channel. And okay, maybe we can conclude here. And we look forward to see you in the next webinar. Thank you.